Good morning. I am glad to welcome all the participants for the fourth day of this 5 days webinar on mathematical perceptions. Mathematical perspectives on computational science and engineering. Today, the first session is by Shri Narendra, lead consultant for Artificial Intelligence Research Group, Wipro, Bangalore. He will be speaking on the topic application of homomorphic encryption in machine learning. He is presently working as machine learning signal and image processing engineer with around 9 years of experience. He holds a master degree with specialization in signal processing and communication from IIT Bombay. His current research includes machine learning, model compression, and Bayesian deep learning. I request Sir to deliver his talk. Sir, please, sir.
Thank you, sir. Thank you for inviting me to take this session. So I'll just share my screen so that everyone will be able to see the presentation. Okay, so is the presentation visible to all?
Yes, sir.
Visible, sir.
Okay, so thanks again for inviting me to take this session. So today I'll be talking on how homomorphic encryption can be used for applications in machine learning domain. So the agenda of the talk is described here. So initially I will explain about why we actually took up this problem, the whole reason behind choosing homomorphic encryption for machine learning. Then I'll briefly touch upon what homomorphic encryption is. So the base of homomorphic encryption is actually lattice-based cryptography. So I will go a little bit in detail on that. Then I will link how homomorphic encryption can be applicable in the machine learning space. Further, I will talk about what are the limitations of the current schemes and how we are trying to overcome them. I will also have some results of the implementation we have done. I will also give a small demo on the same so that you get a feel about how we can use this in our applications. I will also give a literature review about the current state of the art work which is being done in this space. And finally, I'll conclude my talk. So starting off, as most of you might know, a lot of data analysis is being done nowadays with use of machine learning and deep learning techniques. So these techniques have become very popular, especially in the areas of computer vision and NLP, which is natural language processing. And the accuracies which are being achieved by these state-of-the-art techniques of deep learning have made these almost like indispensable. So if I nowadays go and ask an image processing engineer to say how are you doing feature extraction for your problem, I hardly see anyone going back to the basic image processing techniques. Now everyone will talk about the latest deep learning techniques which are being used to extract features. So thus such is the popularity of these. So because of this, now there has been thought of using these in some sensitive domains like finance and medicine. So for example, if you talk about finance, there might be cases where artificial intelligence may be used to maybe determine whether you are good enough to be granted a loan or not. And to come up with these answers, people rely on analysis which with data of a particular person which they might find sensitive. So if someone wants my credit card history, I might find it uncomfortable to share that information, even though they are using it for analysis purposes. So when it comes to personal financial information being shared, there is a hindrance or a blockage. Similarly, when it comes to medicine as well, some of the fields, some of the questions which might be asked regarding the patient's history might be uncomfortable. So some a basic example would be, if I want to do an analysis with patient's data, and one of the questions is whether you are a HIV positive or not, the person might not be comfortable sharing that information. So all these are now kind of hindrances to latest technologies in these domains specifically. So the problem is of privacy. So how do I overcome this problem of privacy? By making people feel comfortable about using their data. So one such solution would be to encrypt our data as such. So if you have your medical history being encrypted and then being shared to the person who's doing the analysis, then I would be much more comfortable sharing that information, knowing that. But the problem is, if I use the general encryption schemes like AES or any hashing kind of techniques, the problem is the whole patterns within the data is lost once I do those encryption schemes. So I cannot use them as is for doing analysis. So can we come up with a solution where we can do some analysis on encrypted data itself? So that is where homomorphic encryption might be the answer, as HE, as we normally call it, will allow us to do some kind of computation on the encrypted data itself. So going further down in the slides, I will explain exactly how this process is possible. So because of this, a lot of research is being happening around using these techniques in the machine learning space. So people are looking at solving these privacy preserving tasks of using machine learning algorithms with the help of homomorphic encryption. So this is still a very nascent idea which is being explored by mostly universities. There are very few industry people who are working on it, but it's a very exciting area to be a part of. So let us come to what homomorphic encryption is. So as I briefly mentioned during the agenda, homomorphic encryption is basically a lattice-based cryptography technique. So I will come to what lattices are and how lattice-based cryptography is being used and what is their security a little later. So let me explain HE with a simple example. Suppose you have two numbers A and B, and say you want to add these two numbers. Now, in general, traditional cryptography techniques, what you would do to preserve privacy would be you encrypt your numbers A and B, and you send it across to the person who wants the result. The person should have a decryption key available. He decrypts it, and then he will do the addition and get the result. But the whole idea about homomorphic encryption is, suppose you have two operations like encryption and decryption. Let enc and dec, as I have mentioned here, we denote the encryption and decryption operations respectively. So what HE says is, addition of A plus B is very simply, you encrypt your A and encrypt your B individually, you add them up and you decrypt it. So basically what you are doing is encryption of A plus encryption of B is giving you encrypted value of A plus B. So there is actually no need for you to decrypt your individual A's and B's. You can add them as is, and the result which you get is actually the encrypted value of the function which you have evaluated, which is addition in this case. And once you decrypt that number, you will be able to get the original information back. So what I am saying is, suppose I have to add say 2 and 3. You encrypt your 2 with homomorphic encryption, encrypt your 3 with homomorphic encryption, add those two encrypted values, decrypt it, and the result which you get is 5. So this is the beauty of the scheme. So what are the steps which are involved? So traditionally in any crypto technique, it has three major steps which are followed. So first is the key generation check, because a homomorphic encryption is a publicly crypto scheme. So there is need for us to generate the public and secret keys. So that is the first part of the scheme. The second part is how do you do the encryption itself, where you convert your plain text messages M1 and M2 into ciphertext C1 and C2. So there might be n such messages. I'm just taking it as an example. So if you take the previous example, your A and B can be your M1 and M2. Then the third part is the decryption, where you convert your ciphertext, which are C1 and C2, back to your original plain text messages, and you would need a secret key to do that. And so encryption is performed using a public key and decryption with a secret key. But the novel part of homomorphic encryption is the fourth part, which is the eval. So what eval does is, it's a very HE specific operation. It takes ciphertext as input and gives a ciphertext as output. The output is what which corresponds to the function of what the input ciphertexts are. So if you take the previous example, the function would be addition, and you feed in your M1 and M2. The eval would do the addition operation on encrypted data and give the result back. Similarly, so some of the use cases where HE is being used is search, machine learning, and there are a lot more which are being used. So there are a variety of functions which need to be evaluated. So what are the types? So homomorphic encryption is coming from a long way back. So initially it was called as partially homomorphic encryption, where uh, uh, where you would be able to evaluate circuits which could do one specific operation. So basically, homomorphic encryption as is supports only two kinds of operations. One is addition, and the other one is multiplication. And what partially homomorphic encryption says is, you can build your evaluation circuit such that it supports either addition or either multiplication, but not both. So an example for this is the age-old RSA. So RSA, as you might know, would be dealing with powers, and you can do the multiplications using the RSA algorithm. And so the second type of HE scheme is called as somewhat homomorphic encryption scheme, which is widely used nowadays. So what happens in somewhat homomorphic encryption is, it allows us to do both additions and multiplications on encrypted data, but only a few number of times. So the depth of your circuit is actually limited. So if you plan to do some n number of multiplications, so there is a limit to how many multiplications or how many additions you can do with somewhat homomorphic encryption schemes. So the last one, which I call as the holy grail, which everyone is running behind, is the fully homomorphic encryption. Because what FHE promises is, you will be able to evaluate arbitrary circuits of unbounded depth, and it is the strongest notion of homomorphic encryption. Because there is no limit on the number of operations I can do. There is no limit on the functionality which I can perform on the encrypted data. So this makes it a very powerful tool to be used in any privacy preserving task. So to solve this, Gentry, who was a PhD student back in 2008 in Stanford, he suggested a method called as bootstrapping. So what bootstrapping does is, it allows us to do these additions and multiplications infinite number of times, but it is a very costly operation, which I'll come to in the further slide. But there is a notion which people are working on, where you can evaluate arbitrary operations with unbounded depth, and this is the holy grail which everyone is behind. So this was the introduction to what homomorphic encryption is. Now coming to what is the basis of homomorphic encryption. So the basis is lattice-based cryptography. So what is a lattice? So lattice is very simple. It is a set of vectors which are linear combination of basis vectors with integer coefficients. So if you see the picture in the slide, you can see that it is a two-dimensional lattice. So if for example, I can choose as the first basis which comes to my mind if I am thinking about 2D is 1 comma 0 and 0 comma 1. So this is the basis, and with this basis I can span the complete vector space of R2. So I will be able to get any point in the R2 space. But lattice is not restricted to complete R2 or complete R3 or complete Rn. You can choose subspaces as well. So you can choose your basis vector, which are integer coefficients, and any linear combination of those basis vectors would result in your specific lattice. So suppose an example would be, instead of 0, 1 and 1, 0, you can choose 0, 2 and 2, 0, and any integer combination of that would again result in a different lattice. So if you see this picture below, I have mentioned two vectors, actually four vectors, two vector pairs, v1, v2, and v1 dash, v2 dash. So if you see v1, v2, v1, v2 is an orthogonal basis pair. So if you take 0, 1 and 1, 0, which is the simplest example you have, it's an orthogonal basis. But basis need not be unique to the subspace or the space you are working on. So there can be another basis, which is v1 dash and v2 dash, which are not orthogonal in nature, but still span the subspace in which you are working. So why this is important, I'll specify with an example next. So now coming to the problem which is being solved using lattice-based crypto systems, it is called as the closest vector problem. So now we know what lattices are. They are integer combination of your basis vectors. The basis vectors in themselves have integer coefficients. And the closest vector problem says, given any point in your n-dimensional space which you are working on, the problem is if you can find the lattice point which is closest to it. So if you see at this picture below, suppose I have this point A, which is blue in color. The aim of my solution would be to find the green point, which is the closest lattice point to that particular vector. So this is a simple representation for a 2D lattice. So I have my blue point. Whether I can find the green or not is the problem I am solving. So let us see what we can do about this. Now, what I claim is, given an orthogonal basis, you can just straightforwardly use Gaussian elimination to identify the closest lattice point. So to understand more in detail, I have prepared a simple example. So now we will consider the same 2D lattice structure which was shown in the previous slide. Now let us see, I have basis vectors a4, 1 and 2, 2. So these are my basis. So if you imagine 4, 1 and 2, 2 in your quadrants, in the four quadrants in the xy plane, you can see that they are almost orthogonal. They are not exactly orthogonal, but they are close to 90 degrees from each other. So what I am saying is, this A and B form a close to orthogonal basis. They are not exactly orthogonal because your dot product is not becoming 0. So, but they are close to orthogonal. Now I have the blue point, which I want to say at 2, 6. So now I know that the closest lattice point to 2, 6 is 2, 7. So now let us see if we can find 2, 7 using Gaussian elimination. That's a simple task which we can do. So now what we do is, since the lattice point is close to since the specified point is close to some lattice point, we will assume that the point itself is a lattice point and find out the linear combination. So what I am trying to say here is, if you look at equation 1, you have your alpha 1, which is the coefficient, integer coefficient, which is multiplied by your first basis vector a, plus alpha 2, which is multiplied by the second basis vector b, which should give you 2, 6. So what I am doing here is very simple. I am taking a linear combination of my basis vectors and seeing whether I can get 2, 6 or not. Now it's a simple, since it is 2D, we can do some simple simultaneous equation solving. And what I get is, you will actually get numbers which are non-integers. So now what you do is, you take those results for your alpha 1 and alpha 2, you round them, and then you see what are the points you get. So now if you solve the simultaneous equations, in this case, you get something like 18 by 135. I don't remember the exact numbers, but once you round them, what you get is alpha 1 will be -1 and alpha 2 will be 3. Now you put these values of -1 and 3 back into the equation 1, and the point which you get is 2, 7. So the claim is, now if I have an orthogonal basis, I can use a simple Gaussian elimination technique, and I will be able to recover the lattice point easily. So this seems to be kind of a very easy problem to solve. So why are we still attempting it? Now let us see what happens if I have a non-orthogonal basis. So the same 2D lattice. Now for the same subspace, I have two other basis vectors which are not at all orthogonal. So if you see the vector a dash is 8 comma minus 7 and b dash is 10 comma minus 10. So both these vectors are in the fourth quadrant, and they are, if you imagine them in the xy plane, you can see that they are very close by and they are not at all orthogonal in nature, which is proven if you take the dot product, which is very large. Now you repeat the same procedure using this new basis vectors, which is 8 comma minus 7 and 10 comma minus 10. So now if you solve the system of simultaneous equations, what you get is alpha 1 to be 8 and alpha 2 to be minus 6. Okay, now I have alpha 1 and alpha 2. I will put them back into equation 2. Now you see the lattice point which I get is 4 comma 4. So what you are seeing now is, given an orthogonal basis, I was able to find the closest lattice point. But given a non-orthogonal basis, I was not able to find the same. So if you have thought about it, this problem is basically boils down to finding an orthogonal basis for a lattice given a bad or a non-orthogonal basis. So a good basis is considered to be one which is close to orthogonal, and a bad basis which is not orthogonal at all. So this is a problem which we are trying to tackle, and the hardness of this problem also makes it difficult to crack. Okay, so this is the closest vector problem. So now you might say that, okay, this seems to be a simple problem. So I'll give you a non-orthogonal basis. You do your Gram-Schmidt auto normalization procedure, get the orthogonal basis. So it will be a simple problem to solve. But the problem with Gram-Schmidt is it works only if you don't have integer coefficients, because the basis which you get, even if you use the Gram-Schmidt orthogonalization procedure, will not be having those integer coefficients which we want, because the lattice is actually constructed by integers and not by real numbers. So there are some schemes like LLL techniques where people are trying to approximate them. But if the dimension of your space becomes very large, this becomes a practical, it's not a tractable problem to solve in polynomial time. So now this is what the lattice-based crypto systems initially thought about. But lattice-based crypto systems need not be limited to the closest vector problem itself. So any scheme, if it can be proved that it is as hard as a scheme which is closest vector problem in the lattice-based crypto system space, if I can prove that my scheme is as hard as it is, then even my scheme is also considered to be a lattice-based crypto system scheme. So it's not that I should formulate my problem in the form of closest vector problem or the shortest vector problem, which is the second problem in the lattice-based cryptography space. But even if I formulate my problem and prove that it is as hard or more harder compared to the basic CVP or SVP problems, then I will still be able to classify my scheme as a lattice-based crypto system scheme. So that is what people did, and one such scheme is called as learning with errors. So learning with errors is a very simple scheme to think about it, to understand. But when you involve all the modulos and things which come together, it becomes a very difficult problem to solve. So let us see what the problem is. So if you see the picture on the screen, so basically it is an AX is equal to B problem which we are trying to solve, where you know A, where you know B, and the red is the secret key in our case, and I need to find that out. Now we solved a similar problem before. You again do the Gauss elimination technique and identify what the secret is. So before I go further, what you can, if you want to actually design your scheme in terms of a pure lattice-based crypto system scheme, what you can do is, in terms of the public key crypto systems, you can choose your non-orthogonal basis as the public key and the orthogonal basis as the private key, so that even you can share the non-orthogonal basis with everyone, and only the person with the orthogonal basis will be able to recover the original point back. So I just wanted to add that point before I go further. So yeah, so coming to LWE, it is again an AX is equal to B problem, where I know A, where I know B, which are both random, which are taken from different probability distributions. And I need to find the secret key, which is in right, which is again a straightforward problem to solve. Now, what variation Regev did to this scheme was, so Regev was the person who initially introduced the scheme to be used. Then what he did was, instead of doing AX is equal to B, what I will do is I will do add a small noise. So it is AX plus E is equal to B. And he provided the proof of the hardness of this problem when using under modulo. So when we use this under different modulo schemes, which I will explain a little later, how exactly you do the encryption and decryption with one such scheme. So this is the basic premise that if you add a little bit of random noise to your already AX plus AX is equal to B system, then this becomes a, and you work in a ring or a group, this becomes a very difficult problem to solve. Okay, so now let us come to how the encryption is being carried out. Now, say I have a message M which I want to encrypt. So this is not exactly the same LWE problem which I described before, but this is one such scheme which is easy to understand, which I have taken as an example. So now I have my message M which I need to encrypt, and suppose my message M has a modulo P. Now I take another random polynomial. So the beauty of all these homomorphic encryption schemes is we actually work with polynomials rather than the numbers themselves. So for an example, what I would do is, suppose I have to encrypt, say, a number, say 2.5. So if my P is 2 in nature, so basically you will represent your individual real number or an integer in terms of a polynomial. So 2.5 can be x square plus 2x plus 3 or so on. So depending upon the encoding scheme which you use, basically you represent your messages in terms of polynomials. Now you have one such message M, which is polynomial modulo P. Now you choose another random polynomial A, which is modulo Q. Q is very much greater than P. Now S is the secret key which I need for decryption, and then I use that again in modulo Q. Now you choose an error vector. So if you see the public key pair equation which I have mentioned here, the first public key PK0, sorry, that should have been the pair should have been PK0 and PK1, not PK1 and PK2. So PK0 is actually just the random polynomial A with modulo Q, and PK1 is what you exactly saw in my previous slide, which is AS plus E, which is what you want. So PK1 is actually the resultant blue vector which you have here. So this is not exactly the same scheme, but the basis of it is the same. Now you have your public key pair. Now there is a ciphertext pair which is associated with it. So how do you create your ciphertext? You take your first part of the public key, then multiply it with a random polynomial u, and you add an error term e, which are both again random in nature, and you scale your message by q by p, because my u, even everything is in modulo q, and all my secret keys are in modulo q, but my message is in modulo p, which is at a lower level. So you just scale the message back by multiplying it with q by p. Similarly, you create your second ciphertext, which is pk1 times u plus e2, which is the second error polynomial. If you have closely observed the ciphertext equations, what happens to the message is just scaling. There is no other operation which is being carried out on the message individually. You are just scaling the message with respect to the polynomial modulo and the coefficient modulo. So this is kind of very interesting to, if I just do the scaling, it is very easy for me to recover the message back. But because you're adding so many random error terms in it, you are actually hiding your message within the noise, which becomes very difficult for us to recover back. And the proof of these hardness have already been published in the papers. So this, if you look at this scheme directly itself, you'll be able to make out that, okay, as I mentioned before, you can do addition and multiplication directly, because even if you add two ciphertexts, so there it will be q times m1 by p plus q times m2 by p. So you'll still be able to get your some added message by just the scaled version of the added message. So you'll be able to do additions on it. Similarly, if you have your messages m1 and m2 and you want to do multiplication, you'll be still able to get q square by p square times m1 m2. So you're still able to get the message back, but the scaled message back. So this is just the encryption part of it. Let us see how the decryption works. So decryption is very simple. So what you do is you take your first part of the ciphertext, you take the second part of the ciphertext and multiply it with the secret key. And use because now my message is in modulo p, but I'm working in modulo q. You scale it back by multiplying with p by q, around it, and you get the original message back. So if I expand these terms, what you see is, if you look at equation 4 carefully, it is basically the scaled version of the message which is getting added with lot of error terms. So basically it is a plus error. So your message plus error, scaled version of your message plus error. Now, if I say that my errors, the random errors which I choose are hard enough to completely obscure my message, but also small enough to get my message back, then this becomes a very powerful scheme. So that is what is happening here, where you take your you add your error terms to the scaled version of the message, scale the message back, take the round version, and result you get is you get the message back. So you can try this yourself. This is a very simple scheme to work with. So as I mentioned before, this is what makes the scheme very useful for addition and multiplication. But if you have observed closely, if you see the equation 4 and say I add two such ciphertexts, what happens is you will get a term qm1 by p plus qm2 by qm2 by p, and here you have three message terms, three error terms. Sorry, even e2 times u, e2 times s. Excuse me. And there will be three terms associated with the second ciphertext as well. So what happens is the more number of additions or the more number of multiplications I do, the number of error terms which get added to my message will keep on growing. And there will be a limit after which I will no longer be able to recover my message back. So this is what somewhat homomorphic encryption says. You will be able to do your additions and multiplications, but only for finite number of operations. You cannot keep on doing additions and multiplications, because what happens if you keep on doing it is the error terms will become bigger and bigger, and there comes a point above which the error terms will completely overshadow the original message itself, and you will lose the relevant information. So this is what is the limitation of a somewhat homomorphic encryption scheme is. And to solve that, as I mentioned before, there is a technique called bootstrapping, where you encrypt an already encrypted ciphertext and decrypt it back to get the original error to be down, to reduce the error which is introduced by the addition or multiplication operation which you are doing. So, but the problem is bootstrapping is a very costly technique. So if you want to try bootstrapping for a simple operation for a small key, it takes around 15 minutes for a single bootstrapping operation, which makes it practically unusable. So a lot of research is also being done on how do we improve the bootstrapping scheme, or how do we make FHE practical. Okay, so now we have our ideas of machine learning, sorry, our idea of homomorphic encryption. So how it is being used, so I can do additions and multiplications on the data, and I am sure of the security of the data. Now let us see how it is used in machine learning. So to understand it, let us consider a simple example of linear regression. So what linear regression says is, it allows us to estimate the value of a target variable as a linear combination of my input parameters. So I have taken an example here where y is a target variable, and you have x1, x2, say xn to be your input parameters. So the linear regression estimate of y is given by equation 5, which is alpha 1 times x1 plus alpha 2 times x2 plus so on alpha n times xn. I have not introduced the bias term as of now, but you can always add a bias term b to the equation 5. Now, what are these alphas? These alphas are the learned weights or coefficients corresponding to input parameters. So now, if I want to estimate a y, what should be the weightage given to each of my input parameters are defined by the alphas. So if you look closely at equation 5, if I have alphas, what is it possible for me to do linear regression on encrypted data? It is possible because it is straightforward, just multiplications and addition. You take your x1, x2, so on, and xn. You can encrypt them. That is my input, which is being fed to the linear regression model for which I need the estimate. So instead of feeding those x1, x2, so on directly, what I will do is I will encrypt my input data x1, x2, so on to xn, and then given I know the weights associated with each of these parameters, you can encrypt the weights as well, or you can keep them unencrypted, because the beauty of homomorphic encryption is you can still multiply a plain text with a ciphertext. So the alphas may be encrypted or may not be encrypted. So what you just do is you take your encrypted inputs x1, so on, xn, you multiply them on encrypted data itself, and you just add them up together, and the result you get is an encrypted value of y. And once the person who has the secret key decrypts it, since it is doing additions and multiplications, you should be able to recover the y as if you are doing your linear regression on plain text data. So the result which you get should match. So this is a very straightforward application. Now let us go a little bit further. The next step, neural networks. Neural networks, as I mentioned before, are the basic building blocks of these state-of-the-art deep learning architectures. And if you break them down into pieces, the basic idea is you have your inputs, you have your hidden layers, you have your output. And the output of each layer is nothing but a linear combination of the input with the weights, which is what we did just now with linear regression. And followed by that, you have your activation functions. You can have a linear activation, you can have a sigmoid activation, you can have a ReLU activation, you can have a tan hyperbolic activation. So there are a lot of nonlinear activations which are being used in the deep learning space. So now the thought is, anyway we are able to do the multiplications and addition. I can still do the linear combination of inputs with the weights. That is already a solved problem. Now if I can approximate my nonlinear functions, then I can still use HE for machine learning tasks. So since the limitation of HE is I'm able to do only additions and multiplications. But if you give me, say, a logarithm of a number, you calculate the logarithm of a number. So the problem is I will not be able to do it directly, because log is not a supported function for my eval, at least in somewhat homomorphic encryption. So what we do is we have to do an approximation. So either you can do a Taylor series approximation, a least square approximation, which I will talk about in the next slides. So you can do some approximations for your activation functions, which are nonlinear in nature, and then you can use them to do your ML tasks using HE. So I have to take the picture is gives a simple example where you can use HE in machine learning space. So there is a client who has he or she has his data, which they need to send it across to the model to get their inference back. So now suppose I don't want to share my data. Suppose the model, if you take the current scenario, suppose I have a model which allows me to predict if I have a disease or not. Okay. So now I send the particular data information, but problem is that data, I am not very comfortable sharing that data with the model. I don't want anyone else to know what the input is, because it has to, if my model is in the cloud will be able to infer a lot of information from my data. So what the client does is he or she uses homomorphic encryption, encrypts the data, sends it across to model. So the model now evaluates everything on the encrypted data itself and gives an encrypted result. So which is same as we did in linear regression. You get your encrypted Y back, and now it is sent back to the client, who he or she has the secret key, will be able to decrypt that particular information and get the inference which they need. So this is one basic use case of homomorphic encryption in machine learning. Okay, all this looks very good and very rosy, and it feels like, okay, I can take it up and I can use it and build my models, encrypt them. I can solve all these privacy preserving tasks very easily. But it's not the case. There are a lot of problems which are associated with HE. So the first thing is the time complexity. So as you know, now everything, all the operations which you do are on encrypted data, and the time it takes to actually compute something on encrypted data is much more as compared to a plain text data. So an example which I have mentioned here is, if you have a simple one layer neural network and you push in your input to it, it can give out in a fraction of a second. But if you use encrypted data, the times might not be relatable, because encrypted data takes much more time. And especially if you are working in real time scenarios where you need your model inferences in real time, it might not be a suitable candidate. Second thing is arbitrary function evaluation. As I mentioned before, we can only do additions and multiplications, and any other functions which you want to perform has limitations because you need approximations. I'll explain about the approximation in the next part. So, but this is a problem, because anytime you do an approximation, you are losing out on the accuracy of the model, because you are not doing the exact computation which is required. So arbitrary function evaluation is still an issue. The third one is the number of computations. And as I mentioned before, I cannot use FHE because FHE requires me to use bootstrapping, and bootstrapping is not practical currently. So I need, if I have a neural network with very huge number of layers, say 100 layers or 200 layers, is it still possible for me to build such a circuit on encrypted data? That is the third limitation, because with somewhat homomorphic encryption, the number of multiplications or additions I can do are limited, and that is what I have to keep in mind when I am designing my model itself, so that I can limit the number of layers to what the scheme can handle. So these are the three major problems in homomorphic encryption currently, and which we are trying to solve. So this is the theory part, whatever I have explained before. Now let us see what is the implementation and what are the libraries which are available, which people can use. Because all the theory is fine, but it has to be implemented and put on a system to see the efficacy of the scheme. So mostly the existing libraries are very new. There is hardly any documentation available for these libraries. So you have to work around, sit on it a lot and try to understand what exactly is happening with each of these functions. And most of them are in C++. A few of them have been ported to Python, but Performance as is slow, and when you port it to Python, the performance degrades further. And as I mentioned, the documentation and support of these libraries is very little. So we have both explored the C++ and Python libraries for our first implementations. So these are few of the libraries which we have explored. The HELib, which is by IBM Research. HEAN is a new scheme which was developed. CL is from Microsoft Research. PySeal and PyFile are the Python versions of these libraries. So they are still in research phase, and as a result, the documentation and support is limited. Now, I mentioned that there is a need for approximation. So let us take an example of a sigmoid function. Now I have a single layer neural network. I have an input. I have a hidden layer. I have an output. And the activation for the IU to the input is fed to the first hidden layer. You do the linear combination, and the output of the linear combination has to go through a non-linear activation function, which is sigmoid. And if you look at what sigmoid is, it is represented by s of x is 1 over 1 plus e power minus x. Now this function I cannot directly use on my encrypted data, because I can only do additions and multiplications. There is a division involved, there is an exponential involved. So how do I handle these different scenarios? So what we did was we tried to approximate the sigmoid. So the first thing we tried was we tried a Taylor series approximation. So if you look at the diagram, there are three lines. The dark blue line is the actual sigmoid. The light blue line is the result of is the result of the Taylor series approximation, and the orange line is the least square approximation. So what we found was the least square approximation is performing better compared to Taylor series approximation. Taylor series is good between values of 0 and 1, but if you are working with higher values, it is a problem. So we decided to go ahead with a least square approximation. In least square approximation, we approximated sigmoid to a third degree polynomial. If you can see, the orange is represented by 0.5 plus 0.15x minus 0.00015x. So this is the approximation of my s of x. And Taylor series, I think, is straightforward. You take your derivative and equate it to at 0 if your x naught is 0. So you have your f of 0 plus f dash 0 by 2 factorial, and you take your series further. So the and if you do that, what you get is 0.5 plus 0.25x plus x cubed by 48. So these are some of the ways you can approximate your functionalities so that you can use them in homomorphic encryption. So what have we done? So we have implemented machine learning algorithms. I think, as I mentioned, linear regression is straightforward. We have also implemented artificial neural networks. We have done convolutional neural networks, recurrent neural networks. So we have covered classification and regression problem as it is. But if you have carefully observed my talk till now, my assumption is the model is already built. I already know what the coefficients are for each of those input parameters. So I know the weights of the model. So the thing which we are trying to focus on is it possible for us to actually compute the weights also on encrypted data? So is it possible to train our machine learning algorithms on the data, on the encrypted data itself? So that is one really interesting challenge which everyone is interested and keen to work on, because that will completely solve the data sharing problem, because you can share it without any inhibition, because you know that your data is encrypted. They will train on the encrypted model in case you want to give your data for a third party to do the training and build a model. So as of now, there are only implementations which are handling inference on the test data for already trained models, and we have done it for regressions and classifications and convolutional networks. Okay, so I want to show a quick demo to get a feel of what using these libraries are for a linear regression problem. So if you can see, how I'm taking a linear regression problem, which is very famous. If you have done the Coursera Machine Learning 101 course by Andrew Ng, this is the example which he says, the Boston housing data set, where you try to predict what is the price of the house given a set of these parameters. So some of the parameters might be what is the crime rate in the particular area, what is the average age of people who are living there, what is the distance from your schools or educational institutions, what is the tax which is being levied. So there are what is the NOx or the pollution levels in these regions. So there are a lot of parameters which are being considered to determine what is the cost of a particular house in that particular area. So now if you see this, we have tried to model this as a linear regression problem. Now taking this data, we have trained a model. So there are 13 parameters in total. And now since we have already trained the model, we know the weights which are associated with each of these parameters. So for the crime rate, I know some alpha 1. For Zn, I know some alpha 2. For Indus, I know some alpha 3, and so on. So each of these parameters have their individual weights which are associated with them. Let us go to the code part. So I have used the PyFHL library, which is the Python version, which is very simple to use for demoing this particular linear regression problem on Boston housing data. So if I run this code, I have created a simple GUI. So the GUI here, if you see, has the input data. The input data is the sample which you select. So now I have to feed in input data for inference, right? So for inference, I choose a sample. The sample will have the parameter values associated with it. So if I say I choose sample number 1. So sample number 1 has some values of crime rate as 8.98, NOx as 0.77, age as 97, so on. So there are some parameters that are associated. Now what I do is I encrypt each of these parameters individually, and I already know the alphas. The alphas are known and I have stored them. I have encrypted them as well and I have stored them. And I'll run the encrypt function. So if you see here, you get something called as encryption is done. So what encryption done means is, now I have encrypted each of these individual parameters using homomorphic encryption with a particular public key. Now, once the encryption is done, what you need to do is you have to do the linear regression. So when I press on the evaluate, what happens is the linear regression function is evaluated. This is the same which I mentioned before. It is alpha 1 times x1 plus alpha 2 times x2, so on, plus alpha 13 times x13, because there are 13 parameters. So now if you see, I have done the evaluation. The evaluation has happened on encrypted data now. Let us see if I decrypt what the result will be. If you see, the result, if I do the whole linear regression on encrypted data, is 32.414334303, so on. And if you do it on the plain text as it is, the value is 32.41433433440 something. So since, if you have thought about the scheme closely, if I had mentioned that additions and multiplications are as it is. But here, if you observe closely, they are equal only up to a few decimal points. After that, they are unequal. This is because homomorphic encryption still works only on integers, because the basis is the lattice based crypto systems. It is lattices which are integer coefficients and so on. So the schemes actually work only on integers. So there will be approximations up to a decimal point, even if you are working with real numbers. So in this case, if I am using 6.21, I cannot use 6.21. Maybe I will do a multiplication with say 100 or 1000, and I'll treat it as 621 or 6210, and then use that number for inference and then scale down correspondingly. So that is why you see a difference between the actual result and the encrypted result and the unencrypted result. But however, they are very close and close to very high decimal places, so accuracy is pretty good. So this is a basic demonstration I wanted to show you so that you can play around with the library and do some simple operations on it. Okay. So similarly, we have done some work on CNNs and RNNs as well, but they mainly use the C++ library because it is faster to handle, and HE also supports something called as packing. So if you looked at the linear regression example which I showed, I was encrypting each parameter individually. But what HE allows us to do is, instead of encrypting each parameter individually, you can encrypt the whole array as a single ciphertext. So they make use of Chinese remainder theorem, and because of it, what they do is they are able to combine a number of an array of integers and pack them into a single ciphertext. And this is very useful because finally you end up doing multiplications with each of these parameters. So suppose I have my encrypted array as a single ciphertext and my encrypted weights as a single ciphertext. Then instead of doing, say, in the example shown below, I had to do 13 multiplications to get the result because there are 13 parameters. But if I pack them up as a single ciphertext, I can get the result in one multiplication. So the speed of operations will be vastly improved, and also packing becomes very much necessary because otherwise it becomes very practically unusable because of the higher encryption times. So packing is a very exciting topic where people are working on unique packing schemes so that you can improve your speed of inference. So coming to the results, so these are some of the results which I wanted to share. Now this is the linear regression example for the same Boston housing data. Now if you see the legends, there are three colors: the result of the encrypted, the result of the unencrypted, and the actual, which the value it should have been if the model was 100% accurate. Now, I'm not able to see the blue line because, as I showed in the demo before, the value of blue and orange are the same. So they are very close together, and they are practically overlapping. So this means that linear regression is straightforward, and the result I get with encrypted data and unencrypted data is the same, and the model accuracies also are the same because they are overlapping. Now let us see the second one. So okay, here before that I'll explain what the x-axis is. The x-axis is the number of samples which are used for testing. So every sample gives out a particular value, and there are hundreds of such samples which I have used for testing, and I have plotted the results of all the 100. Now coming to the next part, where I do the same. Excuse me. Now I use the same data set, but instead of using a linear regression, what I do is I build a simple one layer neural network for the same Boston housing problem, and I use a sigmoid activation function. Now if you look at the results, you see that now there is difference between the encrypted model and unencrypted model. This is because now I have approximated the sigmoid with the third order polynomial. Now even after approximation, you can see that the patterns are still matching. The values are some way off, but the patterns of the results are still matching. So the approximation, as I mentioned before, will definitely reduce the accuracy of the model because of the difference between the actual and the approximation. But still, it is usable because if you look at any classification problem, if my result of my inference is 97%, and if the result of inference on encrypted data even comes down to 90%, I'm still okay because the confidence is high. So because of that, those kind of scenarios which are involved in machine learning, the exact values might not be very much required, and close by values are still will still be able to give us good accuracies. And now we trained the same with a two-layer neural network. You can see now that the values are now farther off than what we saw in the single layer neural network. So here the model is better because we have two layers of hidden neurons. But there are two approximations which are done. One is for sigmoid in layer 1 and one is for sigmoid in layer 2. And because of that, the results are a kind of mismatch. So coming to summary of what we have done now. So we have used homomorphic encryption and applied it to our machine learning problem. We have taken an already trained neural network. We have provided inferences for the same. You feed your test input to the neural network, encrypt it, and the neural network will push out an encrypted result, and you take the decryption of the result and see if it is you get same accuracies. So we have done regression and classification tasks on the same, and we have done up to 2 layers of neural networks. We have also tested it on convolutional neural networks and recurrent neural networks. Convolutional neural networks are a good case study for HE because we are able to get very good results. But recurrent neural networks are still a challenge because, as I mentioned, we are using only somewhat homomorphic encryption, and recurrent neural networks will we have to go back a lot of time steps basically to get the result back. So the number of multiplications involved are huge, and so RNNs are still a challenge. Though we have implemented them up to a certain time step back for a time series data. So this is the one thing. And nonlinear activations, as I mentioned, we have used Taylor series approximations and least square approximations to approximate those nonlinear activations. Not all are very successful. Sigmoid was lucky because we were able to find a good least square approximation. But ReLU is a very tough one to approximate because it is not differentiable at 0, and that becomes a problem. So any least square approximation you get is not of good quality. So approximating these nonlinear activation functions is also a challenge. And the last problem is the number of layers which I can use. So as I already mentioned, you have to decide the number of layers based on the size of your network, based on the size of your problem, because the number of multiplications are limited, and also the type of activation function. Because if you say that I have my number of multiplications limited to 10, and you have your sigmoid approximation itself up to 5th degree, you lose out on five multiplications there. So we have to be very careful in balancing the nonlinear activation approximation and the number of layers which you want to use to get the results. So these are some of the results which we have. So coming to the literature survey part, so as I mentioned, a lot of interest is there in using HE for neural networks. However, the problem, as I mentioned, are of imploding errors. So the errors will add up or multiply with each operation, which each addition or multiplication operation you perform. So we have to be very careful. So as a result, a lot of work has been done on inference of using HE for inferences rather than training. One such good paper, which if interested, you all can look into is the CryptoNets. This was one of the first papers released by Microsoft Research, which used the C library inferring on the MNIST dataset. So MNIST is the handwritten dataset, handwritten digit dataset, where you have handwritten 0 to 9 values. So it's a 10 class classification problem. And they applied, they encrypted the input images, and they built a 2-layer convolutional neural network. And they did so. Again, if you look at convolutional neural network, it has its own set of challenges, because you need to do convolution, which is similar to linear combination of your input, but you need to do max pooling, basically to reduce the size of your input image. So max pooling cannot be done because max operation again is not performed. And so what you do is, instead of max pooling, you replace them with average pooling. because you can do averaging, which is just addition and division. Division you cannot do, but if you know this kernel size, you can have a predefined encrypted value of, say, if my kernel size is 4, so I can do 1 by 4 and multiply it by 0.25, because the multiplication is still possible, division is not possible. So average pooling. And the papers in CryptoNet have completely changed the activation function itself. So instead of using ReLU, what they use a square activation function. So there they save a lot of multiplication operations, because they are using only just one multiplication for nonlinear activation. So if I was using sigmoid, it was x cubed. It's a third degree polynomial which I was using, and I needed to multiply 3 times. But since it is only square, it is just multiply it with itself again. So they are saving on the number of computations in that manner. It's a very good paper to refer to. So now the second part is whether we can train our neural networks on it. So training, as you know, involves backpropagation, and it has to be run on a number of epochs. And as a result of it, there are a lot of multiplications which you do with each operation. So every epoch you have your multiplications going on, and as a result, the number of multiplications are not at all possible to be handled by somewhat homomorphic encryption. You need to bring in the bootstrapping part for it. So a lot of research is being done there. Again, the paper 3 which I have mentioned deals with, again, IBM research people who have given a first cut of training, but it's still not practical and very far off from usage. So, but there are efforts which are being made to train neural networks on encrypted data. So if I want to do training, I have to solve the problem of bootstrapping. So bootstrapping is a good solution, but not practical. So what people are doing is there are a lot of universities who are working to see if I can improve the speed of bootstrapping. As I mentioned, simple bootstrapping takes around 15 minutes for a small key size. So if you want to do it for a bigger key size or a bigger network for training, it becomes practically unusable, because neural network training itself takes a lot of time, and doing it on encrypted data will make the time go 100 times higher, at least 50 times higher. So this becomes a big problem. So there are some papers which are addressing this problem as well. So coming to the last part of my presentation. So basically, I tried to give you a brief of what homomorphic encryption is, what are lattice-based crypto systems, how homomorphic encryption can be used in machine learning. So this is what I had in mind when I wanted to express my views on this topic. And now FHE, as I mentioned, is the holy grail. It's the ultimate prize which one is looking for, because if we are able to solve the practicality issue with FHE, then there are a lot of real world applications which are being so which can be used for HE can be used for these real world applications. So as I mentioned before, the aim is to find a way to solve these limitations of the technology, because once you have the industries using these techniques, it has to be robust. I cannot say that okay, I can do the inference on encrypted data, but you have to wait for a minute to get the result of a single inference. So that is not appealing when it comes to industry. So if we solve the limitations of the technology, then I feel that homomorphic encryption has a very big future, and it can be used not only in terms of machine learning, it can also be used in variety of tasks, because actually the first step of HE in industries is being taken in encrypted search domain, where people are trying to send encrypted queries over the database. So suppose because a lot of people are concerned about what we search on Google, because Google or any other search engine collects information and basically makes a profile of you based on your search history. So what people are trying to solve there is do an encrypted search. So you have your query which you want to send across for retrieving the information. Instead of sending the query directly, you do an homomorphic encryption on the query itself. You send across the encrypted query, and the encrypted query will search through the database. Again, the database can be encrypted or unencrypted depending upon the type of query and the type of system which you have designed. But if it is possible for us to do that, then a lot of privacy issues will be resolved. So the first step in homomorphic encryption is being taken in the search space, but we are trying to focus on using it in the machine learning space. So I hope I was able to give my ideas and share my views across to you in a good way. And I would like to conclude my presentation with the same. So if you have any questions on the same, I would be glad to take them and answer them to the best of my ability. Thank you.
Yes, sir. So please unshare the screen, sir.
Sorry, sir. Can you come again?
Please unshare the screen, sir.
Yeah, sure. I'll do that.
Sir, thanks a lot, sir. Hello, are you hearing me, sir?
Hello. Yes, sir. Thank you very much. It was a pleasure.
Yes, sir. Sir, few questions has been asked by our viewers, sir. Hello?
Sure, sir.
So,
Hello. Yeah, please go ahead, sir.
I'll raise the question, sir, please. Sir, one P. Sharada has asked a question. What are the mathematical concepts which are needed for cryptography apart from number theory and linear algebra?
So if you look at only homomorphic encryption in isolation, I think number theory, ring theory, and linear algebra would be sufficient. But if you look at cryptography as a whole, then there might be other domains which would need to be explored.
Concepts of probability all will may be required.
Yes.
Sir, another question. Any asked by Nasiruddin, any open source tool to evaluate?
So I have mentioned in my slides. So there are a couple of C++ libraries, which is Seal and Helib. One is by Microsoft Research. The Seal library is by Microsoft Research, and the Helib library is by IBM Research. So these are the ones which are mainly being used, and they are open source. So, but the only trouble is there is not much support for these libraries which are available. So you have to dig in deep and look at only a few examples which are available in their repositories to understand and implement it on your own.
Sir, one more question, which is a supplement to this question. I feel that it is asked by Dr. Kokila Ramesh. Can we do this? Can we do this in the tools such as Octave and MATLAB?
No, not currently, sir. As I mentioned before, HE mainly deals with polynomials, and there is something called as the NTL library in C++, which supports which basically it's a number theory library. And currently there is no support available for MATLAB or Octave or any such higher level implementations. Even Python is lagging behind, so MATLAB is still way off.
Sir, I have a doubt, sir. Hello?
Yes, sir. Please go ahead.
Sir, the thing is, this number of layers, what we are going to introduce, if we take any problem in a neural network system, is there any criteria how many has to be included for any problem that we take?
So there is no such criteria as such. So generally what we do is you start off with a fewer number of layers. You train your network with that and check if your model is overfitting or underfitting. So basically underfitting is your accuracies are still decreasing your training accuracy is still decreasing, but and your validation accuracy is also still decreasing. Validity loss is still decreasing. Sorry, not the accuracy. So if it is still decreasing, then there is an option for you to increase the number of layers. Or if your test accuracies are bad and your training accuracy and validation accuracies are good, so there is again another option of increasing. So basically, it depends on the problem. But the basic step would be you start off with a less number of layers, and depending upon your training and validation accuracies, you go ahead by increasing the layers or changing the activation functions and so on.
Sir, thanks a lot, sir. They are the questions which are there asked by our viewers. Sir, very high informative talk, very impressive talk that you have given, sir. Thanks a lot, sir, for accepting our invitation. Thank you, sir.
Thank you very much, sir. It was my pleasure.
Thank you, sir.